So now we'll finish off these last couple of examples from problem 8. So if I'm looking at problem H, what I see is that there's an inside function that's being raised to this power, and the derivative of that inside function, or some multiple of it, is sitting around on the outside. So that's a good hint that we're going to be using a u substitution. I'll go ahead and let u equal the inside function. That would mean that du is equal to the derivative of that right-hand side times a dx. And again, because we're trying to get rid of this dx and the derivative of this inside function doesn't exist cleanly on the outside, what I'm going to do is I'll solve for dx. So if I wanted to get this dx by itself, I would divide both sides by 2x. That would give me a du over 2x is equal to dx. And this will help me compute the antiderivative. So I'll start by just focusing on the antiderivative, and then we'll worry about the evaluation step at the end. So I just want the antiderivative here. In terms of my u's, I know that the inside function is a u, so this is just a u cubed, because that inside function is a u. So actually, I think those parentheses are maybe a little confusing, so I'll just write it as a u cubed. And then the dx out here, I know I can replace with a du over 2x. So the x's here are going to cancel, because I have 1 in the numerator and 1 in the denominator. So this would end up being a u cubed du over 2, if you want to write it that way. Now that over 2 is just going to be around for the ride, so we would, if you want, we can put the 1/2 out here. But we would then integrate u cubed, and that would give us a u to the 4th power, because we increment the power by 1 and then divide by 4. So this will give us a u to the 4th divided by 8 altogether, if we just multiply the numerators and denominators. So this would be u to the 4th plus 8, or sorry, u to the 4th divided by 8 plus a c. And then we should back substitute the original value of u, which was x squared plus 1. So we'll get an x squared plus 1 to the 4th power divided by 8 plus a c. So this is the family of antiderivatives here for any value of c that you want to choose. But because we're doing a definite integral, we can sort of ignore c here. We don't need it for the evaluation step. So if we wanted to return to the original integral, we're integrating this thing from 0 to 1. We just found the antiderivative. We know that one antiderivative is x squared plus 1 to the 4th power divided by 8. And now we're going to evaluate that from 0 to 1. So if we plug in 1, then on the inside of the parentheses we would get a 2. So that's a 2 to the 4th divided by 8. And if we plug in 0 into the antiderivative, we would just get a 1 to the 4th, which is a 1 divided by 8. Okay, and this actually does clean up quite a bit, so this would end up being 16/8 minus 1/8, and that would be 2 minus 1/8. Or if you'd like 15, nope, there we go, 15/8. All right, so lastly, let's look at I here. So I is another one where you could consider using a u substitution, but it's probably not the right idea here. In cases like this one, where you just have a single term in the denominator, it's usually a good idea to just split this into multiple fractions, because each term that you'll get out of this will end up being a power of x, or a multiple of it. So in this case, again, I'm going to focus first on just computing the antiderivative. So I want the antiderivative of negative 3x cubed plus 7 divided by this square root of x to the negative 1st power. Let's first focus on just trying to simplify the thing in the denominator. So the numerator is nice and simple. In the denominator, I have an x to the negative 1st power, and then I'm taking a square root of that. So I'm raising that to the 1/2 power. So this would be an integral of negative 3x cubed plus 7 divided by, whenever you repeat exponentiation, you would multiply those exponents. So the thing in the denominator is an x to the negative 1/2 power. Now remember that we can bring things like this into the numerator if we want by negating their exponents. So I can keep the stuff in the numerator And then if I wanted to bring this term into the into the numerator with the others, then I would negate its exponent. So that would be an x to the negative negative 1/2, which is a positive 1/2. And now we can distribute this. So I'll distribute the negative 1/2 power for x into each of these terms. So for the first one, that's a positive 1/2 power. So this would be an x to the third power plus a 1/2. Because whenever you multiply x cubed times x to the 1/2 power, you should be adding those exponents. So that's what I would get for the first term. The second term will just end up being a 7 times x to the 1/2. And then lastly, there's an integral sign out here. And then lastly, a 3 plus a 1/2 would, I guess, be 7/2. So this first term would be a negative 3 times x to the 7/2 power plus a 7 times x to the 1/2 power. And now this is something that we can integrate. So because we didn't need to do a u substitution here, it's actually okay to just keep the integral bounds throughout. So if you want, you can copy down all of the integral bounds. I'm okay with you omitting some of them, but it's technically correct to put the integral bounds throughout all of these, because if you omit the integral bounds anywhere, then you're just computing a general antiderivative and not a definite integral. So if you want to be super technical about it, then you would put the integral from 1 to 4 everywhere. So that's what we want to compute here. For that, we'll compute the antiderivative. So I want the antiderivative of this thing. The negative 3 is along for the ride. I should add 1 to the exponent. So 7/2 plus 1, which is 7/2 plus 2/2, would give us 9/2 as the new power. And then we should divide by the new power. And similarly for the second one, the factor of 7 is along for the ride. We should add 1 to the power and then divide by the new power. And then this should be evaluated from 1 to 4. And I think I'm just going to skip this step because I'm pretty sure I'll run out of room over here, but the point is just that you would plug in 4 into your x values for this antiderivative, and then you would subtract what you get whenever you plug in 1. And notice that here you could actually compute those by hand, because these fractional exponents are just going to be taking square roots in addition to raising to the 9th or 3rd powers. And we know how to take the square root of each of these bounds of integration. So you could actually compute this by hand, but again, I'm not going to make you do that.